Linearly dependent and independent vectors. The question here is, given the point Q, 3 minus 4, 2, which lies in R3, draw the corresponding rectangular prism and label points M, N, O, P, Q, R, S, T with their respective coordinates. So this part I've done in a couple of videos, and in one of the videos I've done a very neat job. So have a look at it and then draw if you have difficulty, right? So this time I'm not going to draw it to the scale. I'll just make a very rough sketch, because here I'm trying to explain you these four questions. The questions here are: name two linearly dependent vectors from this rectangular prism, okay? Name three linearly dependent vectors, name two linearly independent vectors, and name three linearly independent vectors. So my major concern here is to understand linearly dependent and linearly independent vectors. So for that, I'm making you sketch this. So what I will do here is, I do notice that the points are 3 minus 4, 2. So if we have a prism here, let's say if we have a prism here, then this will be on that side, correct? Because point 3 is, we will go 3 units on this side, 4 there, and then we'll have a prism on this side of our Cartesian plane, R3, right? So what I will do here is that straight away I will kind of sketch my prism, right? So this prism will be 3 units here. Let me do that. 3 units here, and then 4 units to the left, right? So that means we got the base now. So 4 units. Let me draw this as a dotted line, right? 4 units, right? So once we do, and then this is the dotted line for my 3 units. So that becomes the base. 3 and minus 4. Now we'll go to 2, which is up, right? So we'll go 2 units up. So we'll go 2 units up. This is my 2 units up. And then we get a point Q here. This is my point Q. So 2 units up, you can go from all the edges. So you get 2 units up. Let me make, okay, I think I continue with this. And then we have this 2 units up. And similarly, we'll go 2 units up along this. And so we have this side, right? And now we'll complete this top here and make our rectangular prism, and that is the back side. So it's good enough to explain the points, right? So Q, R, S, T. So let's say, so again, M, N, let me call this as M, N, O, P. So that becomes our rectangular prism, right? Now the question here is, name two linearly dependent vectors. My suggestion is, make it to the scale and choose a scale of 1 centimeter used for 1 unit, and do a neat job. Now then answer the questions. Name two linearly dependent vectors. Now what are dependent vectors? Dependent vectors are vectors which are parallel, which are collinear, which are in the same direction, for which the scalar product exists, right? Vector for which the linear combination could be 0. So those are linearly dependent vectors, right? So many conditions I have told you, right? So linearly dependent means what? Parallel, collinear. So two vectors, scalar product, they are scalar products. And the linear combination is 0. That means AU plus BV equals to 0. All these things, any one of them, if you prove, then they are linearly dependent. And they can't do? They can't, right? They can't span. That is most important, since they are in R2. We are talking about two vectors, right? They can't span in R2. This is all about linearly dependent vectors. So this is all about linearly dependent vectors, correct? Now if they are independent vectors, then they are not parallel, they are not collinear, scalar vectors they are not, and this is not equal to 0. And they can always span in R2. That is for independent vectors. Okay? So just the reverse of this. So if the vectors are not dependent, they are independent. Now here, so we'll use this color to show the vectors which are dependent. So all parallel lines, for example, let's go this. So this is parallel, right? So they form, these are, for example, dependent vectors, right? Similarly, if I have these lines here, they are dependent vectors. So that is how you can give dependent vectors. Now name three linearly dependent vectors. Now three linearly dependent vectors will be those who are in the same plane, right? There the criteria is if they are in the same plane, then it is fine. Then they can be written as a linear combination of one another. That is the beauty, right? If you can write as a linear combination, that means they are linearly dependent. If you can't, then they are not. So here, for example, I could have this face, right? So one vector like this, one vector like this, and the third vector like this. All these three vectors are in one plane. Now, important thing is, these vectors in one plane can span in this plane, but not in R3. But they can span in this plane. Right? That is kind of important. So that is what is three linearly dependent. They are in the same plane. But if I am saying three linearly independent, let's talk about three linearly independent. So that could be something like this. So these are not in the same plane. Do you see that? Now these three which are independent, they can form bases, right? So they can form bases, or they can span in R3, right? Span in R3. So that is kind of important. So those vectors, three vectors, which are linearly independent, can form bases for R3. So like that you can get so many combinations here. Do you see that? You can get this one. So like that you have to select three vectors which are in different planes. If you get that, then they are linearly independent. I hope with this you have understood the topic of linearly dependent and independent vectors, whether we are talking about two vectors at a time or three vectors at a time, correct? And how it relates to basis or spanning, right? So two vectors can span if they are independent. Three vectors can span if they are independent. That is kind of important, right? So I hope you understand all this. That's good. Thank you.